No? Hey. Hello, my name is Martinez, and I'm here representing Challenge 2013 for the class Math 2000, and I'm going to solve this problem 32, which is suppose that T is a one-to-one linear transformation. So show that if a set of images, which is this set of the vectors T of the vector v1 all the way up to T of the vector vp is linearly dependent, then the set of just the vectors is also going to be linearly dependent. So in order to show this, I'm going to let the set that was given to us just be S. So if S is linearly dependent, then that means that this set can be written as a linear combination, which is basically represented by this equation that I have here, where I'm taking the last term of the set and I'm writing it as a summation of each vector, of each other vector in the set, times some arbitrary constant C, where not all of these constants are 0. Okay, so now that we have this, we have to try to shape this into a form that we're going to be able to show that this is also linearly dependent. Which means that we're basically just trying to take this and make it so that just VP, just the vector VP, can be written as the summation of just these vectors times some arbitrary constant C, where not all of these constants are 0. That's basically just the definition of linear dependency. So in order to do this, we're going to look at the definition of a linear transformation, which basically says that, let's say we have the linear transformation of C1 times the vector U plus C2 times the vector V, and that can be rewritten as this. And that has to be true in order for this to be a linear transformation, basically. Okay, so now that we have that, we can simplify this in a form that'll end up being T of C1 times the vector V1 plus all of these vectors that are inside, times plus T of Cp minus 1 Vp minus 1. And this is P minus 1, just to clarify, this is P minus 1 because I'm just saying that this is the last vector and this is every single other vector before it. So now that we have this, we can simplify this a little more. And this is just going to equal T of C1 times the vector V1 plus all the vectors inside of it plus C is P minus 1 times vector Vp minus 1. Okay, so now we basically have that T of the vector Vp is equal to T of the summation of all of the vectors times the arbitrary constant again. Okay, so now we have to look at the definition of a one-to-one linear transformation. And that basically just says that if we have T of the vector x, and which equals T of the vector y, this is a one-to-one transformation if and only if x of the vector x equals the vector y. Because a one-to-one transformation just means that it's like a function. Like if you have one value that you plug into the function or in the domain, let's say x and y, then if you plug it into the linear transformation, each value, you can't, T of y will only equal T of x if the vector x equals the vector y. That's the only way that'll be a one-to-one transformation, because that means that each one value x will equal one value y. So like if these weren't the same, then both of these, both x and y, which were different values, would equal the same value, and that means that it won't be a linear transformation. So with that being said, we can say the vector Vp can equal the vector x, and this huge summation of vectors can equal the vector y, and it's basically just analogous to all of this that we have here. So, in conclusion, we can just basically say that, we can say that the vector Vp is equal to C1 plus Cp minus 1 times the vector Vp minus 1 And this, again, is just based on a definition of a one-to-one linear transformation. So because of this, this is basically a linear combination of the set that we have over here. And since this can be written as a linear combination, then we can therefore say that the set V1 all the way up to VP is linearly dependent. And that has been shown. Thank you. I'm Andres Martinez.